Hello everyone, today I am going to talk about our work, Zero-Knowledge Location Privacy while Accurate Floating Point SNARKs. I am Cheng Wu, and this is a joint work with Jens, Luca, Philip, and Sebastian. Location-based services are ubiquitous in our daily lives. We use gadgets with location sensors, like mobile phones and tracking devices. And small pieces of location data are collected to create large datasets for maps, cellular networks, and transportation. These datasets are processed and analyzed in geospatial tools such as DuckDB and Snowflake, as well as applications such as Uber. However, they often fail to protect the privacy of users. We have seen in recent years that these services may inadvertently or intentionally leak sensitive location information. Thus, a natural question is, can we only disclose approximate regions for utility while hiding the exact location for privacy? To address this, our solution is to obfuscate the location first and then prove the obfuscation in zero knowledge. So how to obfuscate location? Given the user's accurate coordinates, we adopt the H3 framework by Uber and convert them into a region with customizable size. H3 is a geospatial indexing system that divides the Earth into cells with unique indices. Compared to other geospatial indexing systems, H3 has many advantages. It uses hexagons as the shape of the cells, which enjoy a lot of nice geometric properties. And H3 also has less distortion than other systems and supports various resolutions, allowing users to control the granularity of the obfuscation. Second, to prove the obfuscation process, we construct SNARK circuit for H3 algorithm based on our new gadget for floating point arithmetic. So what is floating point? It is a way to approximately represent real numbers in computers. Floating point values contain three components, the sign S, the exponent E, and the mantissa M. Most of floating point values are normal numbers, and in this case, they represent the real number in this way. We utilize floating point rather than fixed point for two reasons. First, lessons learned from the Ariane 5 disaster and the Intel Pentium FD bug show the importance of accuracy and standard compliance. Second, H3 involves very large and very small numbers, but fixed point cannot handle them well. As we will see, even with more bits, fixed point still achieves less accuracy than floating point, breaking the correctness and soundness. Now let's see the construction of our circuit. For floating point primitive operations, our gadgets follow a four-step recipe. First, we compute the intermediate sign, exponent, and mantissa values based on the concrete operation. Then, we normalize the intermediate mantissa so that its bit length is bit M. Next, we round the normalized mantissa. The default rule of rounding is round to nearest and ties to even. This process can be determined by three bits, the guard bit, the round bit, and the sticky bit. Finally, we handle the special cases, such as division by zero. With our floating point gadgets, we then build the ZKLP circuit by following the H3 algorithms that map the latitude and longitude to a cell. We summarize this process in 4 steps. And as we can see, they are quite complicated, involving the conversion among multiple coordinate systems. During the conversion, we observe that there is a huge number of trigonometric function computations. To improve the efficiency of our circuits, we leverage various optimizations. A standard technique is to use non-deterministic advice or hints to save the circuit size. Taking division as an example, we do not emulate the division operation in circuit. Instead, we ask the prover to provide the quotient Q and the remainder R as hints. Then, the circuit only needs to enforce the equality between X and Q times Y plus R. We also modify the floating point representation to make it more efficient in circuit. For example, we avoid handling subnormal numbers separately by allowing the exponent to underflow. Furthermore, we remove the bias from the exponent and store the mantissa with explicit leading 1. Lookup arguments are also used to minimize the costs for range checks and power of 2 computation. We additionally reduce the frequency of lookups. For example, in right shifts, the naive approach requires 2 lookups to check the range of the remainder, while we reduce it to 1 lookup by left shifting the number first. This technique also applies to the rounding process of floating point numbers. Finally, we eliminate the costly trigonometric functions. For example, we can remove this arc sign and this tangent by using trigonometric identities. We do the same during the computation of the 2D coordinates, resulting in this, where most of the remaining trigonometric functions can be pre-computed. In our evaluation, we start by testing the compatibility of our circuits with existing implementations. For our floating point gadgets, we generate test cases from the Berkeley test float library, and our gadgets pass all of these tests. We also test our CKLP circuits against the H3 implementation in C. You can see that with float 6.4, the results are all green, meaning that they are consistent with H3. On the other hand, our baseline circuits with fixed point produce mismatches even with more bits than floating point. For performance, our floating point gadgets are quite small and part of the lookup constraints can be amortized. This means that with more operations, the average cost per operation will be smaller. Our CKLP circuits are also highly efficient. They have much smaller circuit size and SRS size, leading to low RAM usage. The proof generation is also fast even on a low-end server as well as mid-range mobile phones. In a concrete scenario of P2P proximity testing, we show that a party can check the distance to 470 pairs per second. However, we note a limitation of our work. Specifically, we assume that the location being proven is authentic. This is not a problem in some applications. For example, in C2PA for content provenance, the camera trustfully cites the authentic location where the photo is taken, and our protocol can be used to obfuscate this exact location. We will also explore several possible solutions, including using Find My Network, signed GPS signals, and TLS oracles to obtain authentic location. That's all for my presentation. Thank you for your attention, and you can scan this QR code for our paper and implementation. Thank you.